How do you do calculus on something that is fundamentally irreducibly random? The answer is ETO calculus, developed by Kiyosaki et in 1944. Today, it underpins every derivative contract on Earth. In ordinary calculus, a derivative is the slope of a curve at a point. Zoom in on any smooth function and it looks like a straight line. That's the whole foundation. But zoom in on Brownian motion and it stays jagged, infinitely jagged at every scale. There's no slope, no derivative anywhere. Ordinary calculus is completely blind to this. We need something new. Start with a coin flip. Heads go up, tails go down. Now flip 1,000 times per second. In the limit, you get Brownian motion, written W sub t. It has three properties that matter. Increments are normally distributed. Expected value is 0, no drift. Invariance equals time. The longer you wait, the more it spreads. Here's the property that breaks everything. In ordinary calculus, infinitesimals squared are negligible. dt squared goes to 0. But for Brownian motion, d minus w squared does not go to 0. It equals d minus t. Exactly. This is called quadratic variation, and you can prove it numerically. Sum up all the squared increments of a Brownian path, and the result converges to t, not 0. That single fact changes everything that follows. To integrate against Brownian motion, we use the same idea as Riemann. Partition time into small intervals, evaluate the integrand, multiply by the increment, sum everything up. But there is one critical difference. We must evaluate the integrand at the left endpoint of each interval, not the right, not the midpoint. Why? Because we cannot see the future. The integrand must only use information available now before the Brownian increment happens. This is called non-anticipating or adapted. The result is a martingale. Its expected value is always 0. The positive and negative rectangles cancel on average. Now the centerpiece. If x sub t is a diffusion process and f is any twice differentiable function, what is df? In ordinary calculus, the chain rule gives f prime times dx, full stop. But watch what happens when we Taylor, expand, and substitute dw squared equals dt. The squared term doesn't vanish. It produces 1/2 f double prime sigma squared dt. That extra term, the ITO correction, has no analog in classical calculus. It exists purely because Brownian motion has non-zero quadratic variation. That is ITO's lemma. Let's use it immediately. Take stock prices following geometric Brownian motion. Apply ETO's lemma to the function f of s equals log s. F prime is 1 over s. F double prime is minus 1 over s squared. Substitute into ITO's lemma. The s squared terms cancel, and you get d log s equals mu minus sigma squared over 2 times dt plus sigma dw. Integrate both sides. Stock prices at time t are log normally distributed. That log normal distribution is the entire foundation of the Black-Scholes formula. Itio published this result in 1944. Merton and Scholes used it to derive Black-Scholes in 1973. The Nobel Prize followed in 1997. Today, $600 trillion in derivatives are priced using models built on this framework. One mathematician, one correction term, one equation that changed the world.